Good evening everyone. Today we will be discussing on biorefinery concept. So let's begin with today's session. So as introduction of the biorefinery, there are some few points that I would like to start with this session. First point is the concept of an integrated biorefinery is what is very similar to the petroleum refinery. In the petroleum refinery, where oil is refined into our various range of or broad spectrum of marketable products, including our chemicals, energy, and fuels. Likewise, a biorefinery also integrates biomass conservation processes and also the equipments, various equipments, just like petroleum refinery, to produce fuels, power, chemical, and value-added products from biomass. So it is very similar to petroleum refinery, but only the feedstock is different, right? So the main difference is that biorefinery are based on the use of the renewable materials that we are considering at the feedstock, that is biomatter, while the petroleum refineries are based on the use of the non-renewable materials. Those are fossil fuels. Those are non those are not the renewable material. But whereas we are considering biomass or biomatter, which is a renewable material, that is the main feedstock for the biorefinery. So when we are talking about the biorefinery approach, it involves multi-step processes, just like other oil refinery. So here the first step is the feedstock selection. Usually, it involves the treatment of the biomass for the further processing, which is called pre-treatment of the feedstock biomass. Afterwards, the biomass, which is subjected to various biological or biochemical or chemical treatments in conjunction with or either biological or chemical, but it involves all of these processes. So, when we are talking about the product driven biorefinery, the biomass will be fractionized into portfolio of bio-based products with maximum value added valuable chemicals, and overall there will be environmental benefits, after which the processes residue, those will be considered for the heat production or power production, which will be used internally or sold to the national electric grids. Those power or electricity which will be produced from the residue of these bio refinery processes, those will be externally used. Those power or electricity can be externally used or internally used for the electricity or energy purpose. So when we are considering the biorefinery, that should be highly energy efficient and make use of the mostly zero waste production processes, where those waste products are regarded as co-products, and maybe those are relocated for added value use or conversion processes. Consolidated bioprocessing and multi-output like biofuel production, biochemical production, and other biomaterials, those process intensification strategies can significantly improve the bioconversion efficiency. Also, this consolidated bioprocessing and multi-output, this concept that will lower the production cost, also that may minimize the energy consumed during the operation, as well as those will reduce the waste output. When we are considering this consolidated bioprocessing and multi-output process intensification strategy. So according to IEA, International Energy Association, there is in general two categories of the biorefinery. One is energy driven, those whose main motive is to produce energy or heat or electricity, and another one is the product driven biorefinery. Next, I will consider a brief of the biorefinery, how it looks like. So, suppose this is our biomass as a feedstock. So, it is taking CO2 for its growth. Also, it is taking sunlight for its growth as a energy. It will store energy. So, when we are considering this biomass for the further production of the chemicals, there will be basically two pathway. One is the biochemical process, and next one is thermochemical process. So, in the biochemical process, there will be lot of other sub further processes, like it will go for pre-treatment, then it may further process in the is enzymatic reactions, then from the enzymatics there will be uh, fermentable sugar production, further goes to fermentation, and there will be lot of products like ethanol, butanol or hydrogen production, right? So if you consider this enzymatic reaction, from there the residue that we discussed in the first slide, the residue, it may be taken to the further step for power generation. Also, this from this residue there will be a significant production of the bio oil. So when we are considering directly the bio mass as anaerobic digestion process, so from that we will get lot of biogas production. From that biogas, it is also main biogas will be produced, and another one will go as a residue part. From that residue, we also uh, can produce the power, also bio oil. So when we are considering this biogas, a lot of biogas is produced by the anaerobic digestion. This biogas is further taken for the purification, and those are considered for synthetic natural gas or methane as a source of this biogas main composition. So this is one part, that is the biochemical process. So when we are considering this thermochemical process, this thermochemical process is considered three steps, like three processes, like gasification process, one is pyrolysis process, and another one is the hydrothermal process. So from the gasification also, it is a um, it is a high temperature process, from where we will get the syngas, and from syngas we can go for the catalytic conversion process or catalytic synthesis process, from where we will get lot of synthetic natural gas. Also, the Fischer-Tropsch process, from where we will get the FT diesel, dimethyl ether. This kind of chemicals we will get, methanol. It is a very important and significant process for biomass conversion. Later one, when we consider this pyrolysis process, from where it is like a low temperature, medium intermediate temperature process. So from where we will get mostly uh, bio oil and solid charred product. Those are further considered for the hydrotreating process and refining process, and from where we will get the hydrocarbons. And this hydrothermal liquefaction process, it is also we are getting lot of bio oil out of this process. So here I briefly discussed about the existing conversion processes. What are those we are doing? We are opting for the conversion processes in the biorefinery for processing the biomass to get the energy or various value added chemicals. For next here we will discuss about what is the main difference between oil refinery and biorefinery. So considering the first point, that is feedstock, when we are considering the petroleum oil refinery, those refinery are homogeneous in sense like those are like when we are getting a petroleum oil from a particular source, the composition of those petroleum that might be homogeneous in nature. Also the other characteristics are low in oxygen content and comparatively high sulfur present in the petroleum oil. Whereas in the biorefinery, the feedstock is lot of heterogeneous process, heterogeneous composition, that biomass, and also those are um, uh, highly consist of oxygen, and there will be trace amount of the sulfur content. The building block composition for the oil refinery, it is ethylene, propylene, methane, benzene, toluene, and xylene isomers. Those are considered to be the building blocks. When for the biorefinery, those are mainly glucose, fatty acid, and xylose. Process type for oil refinery, it is thermal and catalytic processes like distillation, cracking, reforming processes, while in the biorefinery, it is biochemical processes different that I have already discussed. Fermentation process, enzymatic process. It also considered thermochemical processes like pyrolysis, gasification, and hydrothermal conversion processes. When considering the feedstock, the oil refinery, you consider the distillation column of the petroleum oil refinery. There we get a lot of products from top to bottom. There are in the by the mean of specific gravity, those are being separated. Like so, gasoline, the separated products are gasoline, diesel, jet fuel, petroleum, lubricant, this kind of oil refinery products we get mostly. Whereas in the biorefinery, we get biofuels like bioethanol, biodiesel, bioplastic, biochemicals. Carbon footprint. So in the oil refinery, we get ultimately a high carbon footprint due to because we are using the non-renewable fossil fuel. By the combustion of the non-renewable fossil fuel, we get lot of CO2 emission. When we are considering the biorefinery, there is lower carbon footprint because we are considering a um, carbon cycle, like neutral carbon cycle for the growth of biomass. Also, when we are combusting those biomass, there will be less CO2 emission. Sustainable biomass is used, then there will be potential carbon neutrality that we are able to maintain over the process. We are going to discuss about the potential biorefinery overview. So, when we are considering the biorefinery, there are mostly the mostly feedstock that is coming from agriculture, or agricultural or forestry, those are lignocellulosic in nature. Okay, so mainly we are getting biomass feedstock from the these two sources, and from these two sources, those biomass are mainly categorized as lignocellulosic crops, or considered to be lignocellulosic waste product. So this biomass feedstock is first taken for the pre-treatment. There are various pre-treatments are available. It will be discussed in the further slide coming. So after the pre-treatment, those are some of the parts should be hydrolyzed, and it is converted to C6 sugar. Okay, C6 sugar also, from the pre-treatment, the lignin part is separated out because it should be taken care separately, and other C5 sugars. So these are some chemical platforms. Okay, C6 sugar, C5 sugars. So from the lignin, it is taken for the gasification, as well as it can taken for the pyrolysis and other separation processes. Whereas C6 sugar, it is mainly taken for the fermentation. C5 is taken for the various chemical reactions. So those may be interconnected, and you can see there are a lot of interconnections are present. So ultimately you are getting mostly the output of the biorefinery, lignocellulosic biorefinery. We are getting biodiesel, methane, hydrogen, ethanol, chemical building other blocks. You can use as a food and feed purpose, polymers and different resins and other biomaterials as a output of the biorefinery. So when we are talking about sustainable biomass preservation, so we need to take care that biomass feedstock that is going to be used in the biorefinery, that preservation of this biomass plays a very important role for the energy efficiency of those biomass feedstock. Okay, so the second generation biomass, which mainly includes that agricultural waste, mostly the lignocellulosic crop residue, forest waste, and also the municipal solid waste, are widely accepted as a second generation biomass. And those are widely accepted for the biorefinery because those are produced as a bulk amount. The second generation biomass, which are readily available and has a great potential for the biofuel and biochemical production. Some of these second generation biomasses are obtained from seasonal plants, thus they are stored for a very long time before its use in the biorefinery. Thus storage method used for the preservation of such seasonal biomass that can affect the biofuel production either in positive way or in negative way. Storage plays a huge role for the energy efficiency of those biomass. So the second generation biomass preservation methods include open air storage, those are widely used, hay system and silage system. When we are talking first about the open air storage, that involves the natural drying of the biomass in the open air condition. This method is very cost effective but it is limited by the rainfall. When the rainfall occurs, so there will be loss of methane potential, and during the storage it is in the wet condition, so there will be aerobic degradation method when it comes in contact of air. So due to this microbial degradation, there will be loss of methane from the biomass. Those methane which can be further utilized for the biofuel production. So this reduction of the methane or the loss of the methane may lead to reduction in the final biofuel outcome or yield. Thus, the efficiency of the biomass will be reduced. So next is field drying. Field drying, so it also involves the it is also involved in the hay system, but the biomass are rolled into round bales before the storage. So this rolling of this biomass into bales that may reduce the air contact, thereby inhibiting the unwanted microbial activity by reducing the pH of the biomass. So when the biomass pH is reduced, so that will inhibit the microbial activity. But again, the problem of the rainfall during the harvesting or during the field drying condition, that may also lead to 60% loss of the dry matter content, and the loss of this substantial amount of dry matter that may affect the biofuel yield in the future cases or in the future production stages. So there is one solution we can consider, that is the ensealing method. So ensealing is a combination of the biochemical and microbial processes for preservation of the biomass under anaerobic condition with the use of the fermentive bacteria that prevents the biomass deterioration. Ensealing process, it occurs in 4 stages. First one is aerobic condition maintained, then anaerobic condition is maintained, then the stabilization is achieved, and last one is the feed out stages. So details of this each processes is greatly, it is detailed way discussed in this journal that I have given the reference here. You can refer to this journal and you can read about how the ensealing processes are occurring in these 4 stages. Those are perfectly described in this journal. So, the ensealing can preserve or increase the methane potential of the biomass by reducing the loss of organic matter below 20%. So, initially, if the rainfall and other disturbance occur, that may cause 60% loss of the dry matter, while when we are following the ensealing process, the loss becomes below 20%. So such strategies are followed by for the sustainable biomass preservation purposes. Next, it when we are considering about um, to utilize the various kind of biomass in the biorefinery, we need to understand that why the pre-treatment technology is very much efficient or very much judiciously we need to select the pre-treatment technology for specific biomass feedstock. Biomass pretreatment technology. So, pretreatment should be the first and crucial step to unwrap the complex molecular structure of the biomass. This pretreatment, various kind of pretreatment, will allow the access to desired compounds of interest like cellulose, hemicellulose, or lignin. Right? We need to break down those complex molecular structure to desired desired compounds of interest, that is cellulose, hemicellulose, and lignin. So, biomass pretreatment technology lead to significant maximization of the value of biomass to produce a large array of energy, fuels, and various chemicals. So the effectiveness of these pretreatment techniques highly dependent on the biomass structure, quantity of the feedstock and various operating conditions. So depending on this figure, we can see that we can classify the biomass pretreatment into three basic routes, that is physical route, chemical route and biological route. So in the physical route, we are having mechanical comminution, irradiation, pulsed electric field treatment, stream explosion, ammonia fiber explosion. These are kind of or various types of physical route that we obtain for the biomass to pretreat before introducing to the biorefinery. So, in the chemical route, there are different routes like acid treatment, alkaline treatment, organosolvent treatment, liquid hot water treatment, wet oxidation, ionic liquid treatment. Ionic liquid or those are also considered to be green solvent treatment, and gamma valeriacetone treatment. In the biological treatment, there are different kinds of microbes like bacteria, rot fungi, acetomycetes. Those microbial treatment are also efficient for biomass pretreatment. So here now I will discuss a little bit more in detailed way for each and every route that pretreatment of biomass occur. First one is physical route. So here the mechanical comminution process that consider milling of the biomass feedstock. Certain RPM 60 to 330 RPM, milling time 1 to 23 hours is take. The conditions of these descriptions depend on the grinder type also. Irradiation, those are used gamma ray irradiation, ultrasonic irradiation, microwave treatment, also the electric beam treatment. Pulsed electric field treatment, those are 1 to 10 kilovolt per centimeter, 100 microsecond, and 1000 to 5000 pulses are basically used for this electric field treatment process. And steam explosion, those are like a mild temperature 190 to 270 degrees Celsius. Residence time is 1 to 10 minutes and pressure is high by pressure 15 to 30 by pressure. And ammonia fiber explosion, anhydrous ammonia is being used, and those are and zero point 0.3 to 2 gram ammonia per gram of biomass is used, and 60 to 100 degrees Celsius is maintained in the process. The next step is the chemical route, where acid treatment. In the acid treatment, where we can use the diluted or concentrated acids like hydrogen, where um, sulfuric acid, hydrochloric acid, phosphoric acid, nitric acid, and also this kind of acids are used in this process conditions. Alkaline treatment also, sometimes it is also needed to maintain the pH of the biomass. So it is used NaOH, KOH, calcium hydroxide, ammonium hydroxide, those are used. Organosolvent, various organic solvents like ethanol, methanol, diethylene, glycol, acetone, butanol, these kind of things are used, and also some external, in the presence of the external catalyst, this kind of pretreatment is occurring. Hot liquid water, it is 160 to 240 degrees Celsius, and 5 minutes to 1 hour it is being pretreated. Wet oxidation process, here water and sodium carbonate is used. Ionic liquid is also, various kinds of green solvents are used in the 1 to 24 hours pretreatment process. And aqueous gamma valerol acetone is used. This is also a kind of chemical treatment process. Biological treatment that I also discussed, that is various kind of bacteria is used, like you can consider here white rot bacteria, brown rot bacteria, soft rot bacteria, depending on like acidobacter or agrobacterium or rhizobium. This kind of selection of this bacteria is also an important factor for the microbial treatment process. So this going to discuss about the biofuel generation. So biofuel generation, based upon that also the biorefinery are classified. Okay. So biofuels are primarily classified into primary biofuels and secondary biofuels. Primary biofuels, those are directly produced from the burning of wood, animal waste, forest and crop residues. Whereas in the secondary biofuels, these are first generation biofuels, that is also called as conventional biofuels. The source of these first generation biofuels are starch, sugar, vegetable oil. These are produced by fermentation process, distillation and transesterification process. The mainly these kind of biofuels, first generation biofuels are considered to be ethanol, butanol, propanol, biodiesels. Whereas in the second generation biofuels, those are made of lignocellulosic crops that we discussed in few slides before, that is lignocellulosic biomass waste or biomass feedstock. Those are highly used for the industry, for the biorefinery purpose, for because we are getting in a bulk amount. So these kind of lignocellulosic crops like rice, wheat, straw, wood and organic waste, they require thermochemical as well as biochemical pre-treatment process, and those produced by and these biofuels are further after pre-treatment, those are further went for the other conversion processes like gasification, enzyme hydrolysis, and fermentation processes. So, major second generation biofuel is considered ethanol, syngas, which is a mixture of carbon monoxide, hydrogen, and hydrocarbons. So, these are considered to be second generation biofuel. Third generation biofuel, those are made of oil extracted from algae and seaweed. Mostly we are getting biodiesel, bioethanol, and hydrogen production. Third generation biofuel, mostly we are getting from algae, microalgae or marine biomass sources. And fourth generation biofuel, it is made of bioengineered microalgae and cyanobacteria with enhanced capability for the CO2 capture. So, from this first generation, second generation, third and fourth generation. So, in this on this generation purpose also, the biorefinery are kind of these are classified. Classification of the biorefinery. Yes, someone wants to ask any question. Jay, you have raised your hand. Is there any question as of now?
Yes, this irradiation. Actually, what is the purpose of that one? And
What? Uh, I couldn't get you. Hello.
My
Please.
voice is audible.
Yeah, now it is audible.
Acha, then in the last slide, you have told that irradiation process in connection with that physical process.
Yeah.
What is this irradiation? What is the real purpose of it?
Um, Wait a minute. So, so this irradiation process that considered that considered to be the gamma ray irradiation or ultrasonic irradiation. So this kind of um basically when we are considering this irradiation process, those gives the high frequency when we are going to pre-treat. Like if you are making a pulp out of the biomass, um suppose we are making the pulp like biomass, and it is mixed with some solvent. So that solvent and biomass should be properly mixed. Okay, so we are using the, suppose in the consider the ultrasound irradiation process. So when we are ultrasonicate the pulp condition, so it is well mixing condition that we are getting. Also, when we are getting the microwave treatment process, this irradiation also is mostly use consider this Haj. So this high frequency treatment is being done. So the biomass composition are a little bit broken condition, like mechanical communication process is some kind of grinding or milling purpose, some mechanical balls and jaw crusher and these kind of things we use. But in the irradiation process, these are high frequency ultrasound processes or gamma ray processes, those that will break the molecules into smaller molecules. So when we are considering the pulp system, so this biomass dipped into some solvent, when we are doing the ultrasound or irradiation process, that that solution or that yeah, that pulp condition will be well mixed, and molecules will not be in the agglomerated condition, those will be in the well dispersed condition. So that will be good for further conversion processes. Suppose that pulp is um, uh, taken for the fermentation process. Okay, microbial fermentation process we are taking further for that treatment. So in the microbial fermentation process, if our feedstock is well dispersed in condition, there is no agglomeration, or the molecules are in the simpler format, now that their complex structure is further broken down into simpler format or simpler structure, then the microbial fermentation, the yield of the desired product will be higher. So this is one kind of the physical treatment that we are doing for the, as a part of irradiation. We can also do mechanical treatment, but for that we are using some different equipment. But in the irradiation, and I would like to mention that irradiation process is more efficient than the usual mechanical communication process, that treatment. So is it okay with that?
Yeah, it's clear. And that same slide, one more same slide. That what is that electron beam? One thing, something is there in the radiation process. Last method,
And that
electron beam treatment.
beam treatment is also
So
categorized in the same process. Uh, so we are using different kind of
that
um, sources of irradiation. One we can use gamma ray, other we can use ultrasound, or microwave irradiation. So if you want to read about details of these processes, I can also give you the reference journal that you may refer in whole to get the detailed
Agreed.
clarification of this process.
Agreed. That electron beam treatment 82,000 kgy. What is that? Kg? Something. That unit is there. I didn't understand. What is that? Kgy. 82,000 kgy. What is that kgy? Any
uh, I'm not sure about exactly because these are let me check.
Okay.
I
Uh-huh.
will tell you in a few
Okay.
minutes.
Okay.
Okay.
Leave it.
Yeah. Okay.
No issue. No issue. No issue.
Yeah. Okay. So next, we are going to discuss about the classification of various biomass conversion processes. Those highly divisions are like biochemical, thermochemical, and physical chemical pathways. Okay. So different feedstock we are considering for measured outcome of the biofuel products. So when you see this table, these connections are well made. So biomass processes, the biochemical conversion, anaerobic digestion, fermentation, and photo biological hydrogen production. Lot of hydrogens are produced by these biochemical processes. So when we are considering the anaerobic or aerobic digestion method, so we are getting second generation, third generation, and fourth generation biofuels. Okay, so major products are considered to be biogas, biohydrogen, bioplastic, biopesticides, ammonia, and VFA. Those kind of major bioproducts are we are getting from this anaerobic digestion process. And while we are getting the fermentation process, we are getting lot of all generation biofuels like first generation to fourth generation. So we are getting bioalcohol, ketone, biolipids, acetic acid, lactic acid, biohydrogen, and acetones. Those are highly valuable product for the chemical industry. Succinic acid also. Okay, so photobiological hydrogen production, the third generation and fourth generation biofuels are produced, and mostly we are getting the hydrogen gas from the photobiological hydrogen production, this process when we are opting for. So the next process, that is the thermochemical process, I already discussed what are the process like pyrolysis, combustion, hydrothermal liquefaction, gasification, and torrefication process, right? So from this also, when we are considering the pyrolysis, we are mostly getting biochar, bio oil. Okay, gaseous production, product production is very less for the pyrolysis process. So we are getting mostly bio oil and biochar. Other we are getting little amount of the syngas and hydrogen production and phenolics. Different phenolics are produced. In the combustion process, we are mainly getting heat, ash, and energy or electricity outcome. Liquefaction process, bio oil is highly produced, whereas biochar production is very less in the liquefaction process. Also we get lot of biogases production. Gasification process, we are getting syngas as a main product, fuel gases, and hydrogen, bioash, and tar. Torrefaction process, where we are getting the biochar as a main product and carbonized material, bio oil, and gases. So when we are considering the physical chemical conversion in a mixture, so here the mechanical extraction or the transesterification process, that is the we are considering that oil to trans-esterificate to biodiesel and biogasoline, and other crushing and grinding pelletizing processes that we are opting for, we are getting mostly the solid fuel. Briquetting and grinding, those kind of thing we are getting as a solid fuel. This solid fuel are further combusted and we are getting heat or electricity as a outcome. So now we are going to discuss about the integrated biorefinery concept. So the conventional biorefinery included the use of the feedstock like corn or wheat. Those are highly consumed by the humans, creating the food security competition as well. So also this source of biomass, whether it is produced sustainability with sustainability, was not taken into consideration. So we are hence the conventional biorefinery has a low flexibility and integration opportunity and resilience. So we need to move towards some integration of this biorefinery with the existing refineries. So integrated biorefinery is a resilient processing facility that transforms the various biomass feedstock into the range of valuable products like biofuels, biochemicals, pharmaceutical products and energy as well. So this infrastructure integration is the linking of the various process units in the existing facility, syncing of a biorefinery with the existing petroleum refinery and or any other CO2 sequestration from the industrial exhaust to grow the algae, where subsequently we can produce the biodiesel. So that I this kind of integration of the biorefinery with the existing petroleum refinery, this approach can take the shape of mass energy and property integration, ensuring a well or coordinated and unified system. So this integrated biorefinery approach is very useful for a sustainable source of uh, chemical production or energy production, because biorefinery itself a very initial stage, this is not well developed in the production of the bulk quantity of the chemicals or huge amount of the energy supply. It is not that much sustainable, so it is advisable to integrate or link this biorefinery with the existing petroleum refinery in such a way. There it is also given one example like the CO2 emitted from the petroleum refinery, it can be sequestered in the form of growth of algae, microalgae. So this growth of microalgae, we are taking CO2 as a growth, as a nutrient, like one of the essential thing for growing the algae. So this kind of CO2 sequestration is being done to grow the algae, and this algae can be further processed for production of the biodiesel out of that. So this kind of integration is very helpful for a well coordinated system. So considering also to reduce the high upfront cost, the integration of new biorefinery concept into the existing industrial complexes holds an interesting pathway if this integration can be done in a sustainable way. So here I have shown one example, like any kind of raw material that we are using. So here only the methanol production that we are focusing, or only the biodiesel production, or only the biosuccinic acid production. So these three platforms are separate. Suppose you consider the three processes are separate, but in an integrated biorefinery concept, we are taking that this raw material is used biomethanol, biomethanol as well as biodiesel as well as biosuccinic acid production. So we are getting one one input, one feedstock from in the different processes, we are getting different outcomes. So this methanol can be taken out of the process and can be sold, but we still further processing, and we are getting biodiesel and biosuccinic acid. So this is one short of example for the integrated biorefinery approach. So you can see in this picture that it considered to be the highest capex, and this is the lowest capex condition. So when we are considering for a new, completely new greenfield biorefinery, it will have lot of investment. So it considered to be highest capex. New biorefinery on a brownfield like lower capex from the shared services such as steam, water, power, storage, and logistics. So this comes down, and at the lowest you can get the co-processing or refocus of the existing plants from the fuels to chemical, like I have already discussed in the last slide, like co linking of existing facility with this new growing biorefinery concept. So from there we can get like we can minimize the capex. We can opt for the lowest capex out of the system. So this is kind of strategy we need to follow for integrating the biorefineries to produce a lot of chemicals out of that, and also keeping the investment low by integrating these refineries. The types of biorefineries which is being proposed by the IEA Bioenergy Tax 42. These are classified into four categories, like by the means of platforms, products, feedstock, and processes. Platforms are C5 platforms or C5 sugar, C6 oil, syngas, biogas, hydrogen, and lignin. These are some platforms on which the biorefinery are classified. In case of the products, when it is energy driven biorefinery, so main products are biodiesel, bioethanol, biomethane, electricity, heat. Also, when it is energy driven, and other one is the material driven or material driven biorefinery. Those are we are getting as output of food, animal feed, fertilizer, glycerin, polymer, biohydrogen, resins. These are some product based biorefinery. And feedstock based, dedicated crops like oil crop, oil refineries, or oil crop based refinery, sugar based refinery, starch refinery, grasses, marine or algae biomasses, lignocellulosic biomasses, then residue based like oil based, lignocellulosic based, organic residue based. So these are some different types of the biorefineries classifications. And processes, like we already discussed about the thermochemical processes, combustion, gasification, pyrolysis, hydrothermal processes, biochemical process, fermentation, anaerobic digestion process. Chemical process is transesterification process, and mechanical process, separation and pressing process. So these are broad category of like broad diversity you can see, based on which it is proposed by the IEA Bioenergy Tax 42, the types of the biorefinery. Now we will consider different kinds of feedstock for biorefinery that is available for further processing. So these renewable carbon-based raw materials for biorefinery are provided from four different sectors: agriculture, which is dedicated crops and residues; forestry, industries as well, like processed residues or leftovers; household, source of municipal solid waste and wastewater; and aquaculture, like algae and seaweeds. The main biomass feedstock can be grouped into three wide categories. One is carbohydrate and lignin, triglycerides, and mixed organic residue from starch, cellulosic, and hemicellulosic source. These are carbohydrates are molecules made up of carbon, hydrogen, and oxygen, and these are by far the most common biomass components found in the plant feedstock. The most important two sugar crops are sugar cane and sugar beet, which together with corn, that is the starch crop, supply almost all the ethanol production that is produced today. Huge production is taken by the help of the sugar crops and starch crop. So the starch, which is C6H10O5 and N number of the chain, is a large polymer molecule composed of many hundreds and thousands of the glucose molecules, which is starch is also categorized as polysaccharides. It must be broken down into two or one or two molecules pieces prior to be fermented. So once sugar have been depolymerized from the starch crop, or these are extracted from the sugar crops, they can be easily fermented to methanol, or they can be used as a substrate for chemical reactions leading to wide range of the chemical products. So the lignocellulosic biomass, which is readily available in the market, has three major components: cellulose, hemicellulose, and lignin. While cellulose and hemicellulose are the polysaccharides that can be hydrolyzed easily to sugars, and later on it can be fermented easily to ethanol. But the lignin content cannot be used in the fermentation process as a whole. Like directly, it cannot be used in the fermentation process, but it may be the other processes like chemical extraction or energy generation process. So here the lignin, which is almost 15 to 25% content of the total feedstock dry matter, is the largest non-hydrocarbon fraction of the lignocellulose. Another one is the oil and fat. These are triglyceride, which typically consist of the glycerin and saturated and unsaturated fatty acid. Like sugar and starch crop, oilseed crops, these are characterized by low yield and high use of inputs. So, MSW feedstock or the municipal solid waste feedstock are more suited for an anaerobic digestion process to generate mostly biogas rather than other fuels or chemicals. So these municipal solid waste are mostly used for the production of the biogas. So uh, mm, uh, these are some descriptions of the different feedstock category. Those are used for the biorefinery. Considering the technological processes in the biorefinery, the aim of the technological process in the biorefinery is to depolymerize or deoxygenate the biomass component. This is the main aim of the technological processes that we are opting in the biorefinery. So there are main two thermochemical processes for converting the biomass into energy and chemical product. One is gasification, next one is the pyrolysis, and third one is the hydrothermal liquefaction process. So mostly thermochemical process, that is gasification, high temperature process more than 700 degrees Celsius, and with low oxygen levels, it produces the syngas, this composition. Pyrolysis, this is the intermediate temperature 300 to 600 in the absence of oxygen to convert the feedstock into liquid pyrolytic or oil or bio oil, you can say, solid charcoal and slightly uh, syngas composition. Unlike the thermochemical processes, the biochemical processes occurs at a low temperature and have a lower reaction rate. So biochemical process takes longer days to complete conversion of the feedstock into desirable product. So this is a very slow process, whereas thermochemical process is a very fast process. The most common type of the biochemical process are usually we go for fermentation and anaerobic digestion process. So mechanical processes are the processes which do not change the state or the composition of the biomass. They only perform a size reduction or separation of the feedstock in the different components. In a biorefinery pathway, they are usually applied first because the following biomass utilization requires the reduction in the material size. So here the reduction in the material size, that we also apply the irradiation process in this purpose. So it breaks down the molecules into smaller molecules, so it the material size reduction is also possible in that by this irradiation process. So whatever it is, then now within the specified range we have reduced the size of the biomass feedstock. So depending on the feedstock species handling and further conversion process, these mechanical processes are selected. Chemical processes are those processes which carry a change in the chemical structure of the molecule by reacting with other substances. The most common chemicals in the bioconversion processes are done by hydrolysis and transesterification, but this group also include wide class of chemical reactions where a change of the molecule formula occurs. A different chemical is produced. So important chemical reactions in the biorefinery, this is Fischer-Tropsch synthesis, methanization, steam reforming and others. Now I will discuss about some of the chemical platforms that is being considered in the biorefinery. So, in comparison to the oil-driven platform molecules like oil refinery, the platform molecules are considered to be ethylene, benzene, this kind of chemicals. But in case of the bioplatform molecules, these have much higher oxygen content. So, this will result in an interesting shift in the chemistries from the often harsh and environmentally damaging oxidation procedures to largely greener reduction chemistry. So, levulinic acid, this is formed by the acid hydrolysis of the C6 sugars and can be converted into a large number of the chemical derivatives. Thanks to its thanks to its high reactivity. Since it has both a ketone carbonyl group and an acidic carboxylic group, it can also react with ketone and fatty acid. So this levulinic acid is further converted into desired product, either chemicals or fuels additives such as methyl tetrahydrofuran, amino levulinic acid, diphenolic acid, and ethyl levulinate. So this kind of chemical platforms is being considered. You can see this diagram. This bio platform molecules are glycerol. Some of the examples are given: levulinic acid, yeah, glutamic acid. This kind of other names are there. You can go for this. These are some platform chemicals are considered for the biorefinery, whereas in the oil refinery the most significant chemical platforms are ethylene, benzene, glycerol, not glycerol, methanol, and these kind of thing are for the petroleum driven refinery. So based upon this chemical platform, these are considered to be platform because many other chemicals are also can be produced from these sort of chemical platforms. So this gives a wide spectrum for the other chemical production. So, the products of the biorefinery system can be grouped into two broad categories. One is material product and one is energy product. The most important energy products which can be produced in the biorefinery are gaseous biofuels like biogas, syngas, hydrogen, biomethane, right? Solid biofuels in the forms of lignin, uh, charcoal, and pellets. Liquid biofuels for the transportation as well. It is used bioethanol, biodiesel, Fischer-Tropsch fuels, and bio-oil. The most important chemical and material products, those are following: chemicals like fine chemicals, building blocks, and bulk chemicals; organic acid like succinic acid, lactic itaconic acid, and other sugar derivatives are used. Polymers, resins, these are also some kinds of starch based plastic, phenol resin, furan resins, biomaterials like wood panels, pulp, paper, cellulose, food and animal feed, fertilizers. So these are some broad category of the biorefinery products available from different source of the biomass as a feedstock. So now we are going to discuss about the model based classification of the biorefinery, that is whole crop biorefinery. So whole crops are the first generation feedstock in the biorefinery industry due to their availability in the initial stage of the development of the production platform, right? So this whole crop include a variety of the cereal, that is starch crop, sugar crop, oil and energy crops. These products from the products from the extraction processes of this whole crop are simply used as the feedstock in the biorefinery to produce several value-added products, including bio-based chemical building different chemical building blocks that are the intermediates in the processing of functional food, pharmaceutical products, textile, plastic, lubricants, biofuels, and others. So here we can see this whole crop cereals. These are first gone for the milling process. So we can opt for the dry milling or wet milling process. So these milling processes are used for mechanical separation of the biomass into this by this process the biomass is separated into grains and straw fraction. So this grain, suppose 20% is grain fraction and straw fraction is rest of the 80%, and these are further converted into different products, right? So the grain will deliver this starch platform. From the grain we are getting the starch, sugar and other raw material. This behaves as a starch platform, and the straw, it will give you the lignocellulosic feedstock um, platform, lignocellulosic feedstock platform. So where we will get lot of from these two platforms, we are getting lot of fuels, chemicals, polymers and other materials, right? So in between whatever be the residue, this can be converted and this can be used for the heat and power generation. This is the scenario for the whole crop biorefinery. So coming to more in details, you can see from the field we are getting the grain whole crop. We are getting the whole crop grain biomass as a feedstock, cereal, corn, maize, and from there we are separating out in the straw and seed portion. From the seed we are grinding it, milling it, and it can be directly used for the decomposition to get out of other binder, adhesive and cement. So the from that milling, from that seed, the other part is when we are extracting the starch. From the starch we are getting biotechnological conversion and chemical conversion processes. We are getting glucose, and by the chemical conversion processes we are also producing sorbitol, glucosamine, acetate starch, carboxylic methyl starch. So we are, you can see the lot of chemical conversion processes we can opt for producing different kind of chemicals out of the seed as a whole crop biorefinery. Out of this, these are the output. And the glucose for the biotechnological conversion, glucose, it is further fermented and it is producing ethanol. So in the straw portion, when we are talking about straw portion, the decomposition, it is producing by the decomposed lignin, hemicellulose and cellulose. Those are further can be taken care of the biochemical conversion, and it can produce this kind of broad spectrum of the chemicals. So this, and another one, this residue can be combusted and it can produce the energy, as well as this kind of residue that we are getting from this seed grinding and milling. This also can be used as a adhesive binder and cement purpose. So this can be used a um, lot of opportunity is there for this whole crop biomasses. So this whole crop biorefinery is very effective. So it comes under lignocellulosic biorefinery as a part of this whole crop biorefinery. I am presenting it is in a separate way because lignocellulosic biorefinery is very important because of its availability as a biomass, lignocellulosic biomass. It is well available in the market as a bulk amount. So lignocellulosic biomass is a feedstock requiring special processing due to its complex natural structure. This feedstock is generally much more recalcitrant than currently used starchy material, just like ethanol industry, which poses further challenges in the processing. Generally, there are two processing routes to convert the lignocellulosic biomass into biofuels. One is thermochemical and another one is biochemical. That we know already. Now, I would like to present the routes. What can be we can achieve from the lignocellulosic biorefinery. So, by this thermochemical process, when pyrolysis itself has three variety, fast pyrolysis, slow pyrolysis and flash pyrolysis, we are getting bio oil, char bio oil and syngas. So from this bio oil, we are getting lot of bio alcohols and biodiesel production. Whereas gasification, we are getting lot of gaseous fuel production. Hydrothermal production, we are also getting bioalcohols and biodiesel production. And torrefaction, we are getting mostly the solid fuel production. So, where in the enzymatic hydrolysis or the biochemical processes, we are doing acetogenesis, methanogenesis. So these processes I have mentioned in the last class also. So we are getting lot of biomethane production out of that. And also when we are doing the fermentation of those sugars, lignocellulosic biomass, after fragmentation we are getting lot of sugars, and those are fermented by the microorganisms. After distillations of the product and dehydration, we are are also getting ethanol, butanol, those kind of bioalcohols, and lot of biohydrogen. So we are getting lot of products out of the lignocellulosic biorefinery. So it is having high potential for compete for in the competition of the existing petroleum refinery. So when we are considering the next type of biorefinery, which is the also model-based classification of the biorefinery, that is green refinery, green biorefinery. So green biorefinery corresponds to sustainable processing of the fresh green biomass, such as fresh green biomass considered grasses, legumes, uh, with high content of the leaf protein and soluble sugars to produce multiple products out of that. So green biomass feedstock is initially fractionized by pressure to obtain two main fractions. One fraction is the juice that is, and another fraction is the cake. So this raw biomass is fractioned into this raw biomass. It is fractioned into fiber rich product that is called cake, and another one is the organic rich green juice. So this press cake is allowed to treat for further for hydrothermal, enzymatic or thermochemical processes to obtain a variety of chemical and biomaterial. Whereas the other fraction, that is the juice, green juice, is treated by the biochemical and other biotechnological processes to obtain miscellaneous organic compounds or other natural products. So protein soluble sugars are there in the organic juice. So out of these processes, whatever be the residue, those are uh, those residue streams from these processes, those are anaerobic digested for the production of biogas, or also this can be used as a heat and power source for the internal use. So this is the overall potential for the green biorefinery. So next is the two platform concept that is very helpful for economic purpose for the biorefinery. Um, the two platform biorefineries have sugar platform and syngas platform. There are two platforms. So the key benefits of a two-platform biorefinery is the optimized utilization of this biomass, as it can produce a spectrum of the bio-based products of chemical, food, and as well as energy. So this is the you can see this is the biomass feedstock. It is having one sugar platform, another one is the syngas platform. So this sugar platform, this sugar, it contains cellulose, hemicellulose, and other C6, C5 sugars. Right? This sugar platform is further treated with biochemical conversion routes. Typically, the fermentation of the sugars is being done, whereas the syngas platform, it depends on the thermochemical methods, gasification or other this kind of methods to produce lot of syngases, and out of this lignin fraction is converted into syngases mostly, and another portion is the lignin. It is mostly converted into syngas. So these two platforms, sugar platform and syngas platform, those is highly used for production of energy and lot of chemicals. So this is the concept of the two platform biorefinery. So you can also see these two platform in a detail, like mostly like whole crop, straw, seeds. These are pre-treated and carbohydrate sources are being formed. It is fermentation is being done. We are getting lot of acids like lactic acid, amino acid, proteins, enzyme, ethanol. So out of this, biogas is also produced. Those are used for the energy purpose. Whereas from this, when the green like grasses and alfalfa, these kind of green biomasses are taken. Those are pressed, and pressed cake is being further processed for the green pellet for fodder or solid fuel, as a solid fuel, raw material for the syngas, raw material for the different kind of production of hydrocarbon, for production of biogas or fibers, or this kind of other raw material for the chemicals like levulinic acid. And also the press cake, these are these are category of the other products derived from the press cake. And for the press juice, that is rich in that is rich in other proteins and soluble sugars. So these are further separated or decanted and or other gone for the fermentation, and this kind of things are also lot of chemicals can be produced. So this is the whole potential for the green biorefinery. So next one is the thermochemical biorefinery. So in a thermochemical biorefinery, the fuels, chemicals, and power are co-produced. Right? In a thermochemical biorefinery, the existing of a platform chemical brings different options for the multi-production of these products. The platform chemicals could be a product itself, or it can be converted into more products. That's why it is called platform chemicals. Thermochemical methods of conversion can be used in an isolated manner or integrated manner with other thermochemical methods of conversion. So there are several advantages of this integration, as they produce more valuable hydrocarbon than it when it is used in the isolation. So when it is used in the integration biorefinery concept, so there we will get more valuable hydrocarbons as a output, because the carbon utilization efficiency of the biomass to required products is increased in that case of integration. Unlike the biochemical biorefinery, which rely on microbial and enzymatic conversion, these thermochemical biorefineries use heat, pressure, and chemical reactions to break down the biomass into valuable reaction in a faster way. This is a method, this is a faster process rather than enzymatic or microbial conversion process. So advantage of the thermochemical biorefineries, these are high conversion efficiency of biomass into fuel. It can process a wide variety of the feedstock, whatever it is, municipal solid waste, forestry waste, or agricultural waste, produce valuable byproducts like biochar and syngas. And also it can be more scalable and flexible than the other biochemical route. So this is the products from the thermochemical biorefinery. Thermochemical process, combustion, mostly heat and gas are produced. Gasification, syngas, that is fuels and chemicals are further processed from the syngas by the Fischer-Tropsch synthesis method. Different chemicals are produced. Hydrothermal upgradation process where we get the hydrogen, methane, and bulk specialty chemicals and other functional porous carbons. Pyrolysis, where we get the bio oil, char, and gases. Where for the upgradation we also get the steam reforming to get hydrogen. Hydroprocessing to produce fuels and other chemicals. So char, these are highly used in the soil amendment process and highly used for the catalyst as a catalyst or adsorbent, this pyrolyzed char. And gaseous, those are used for steam reforming to produce hydrogen, because hydrogen is a uh, high highly energy efficient fuel. So a lot of hydrogen can be produced by this thermochemical process, but it takes lot of conversion steps. The next model based classification, that is algae biorefinery or microalgae biorefinery. So recently, the microalgal biotechnology industry has attracted lot of attention due to the development and application of the biorefinery, which allows for the production of wide range of products from the same harvested microalgal biomass in as little few days, including high chlorophyll or carotenoids or carbohydrates, lipid, protein, nucleic acid. So among these others, so these are the biotechnological industry is growing like this way. So biorefinery based on the microalgae have made significant strides in the conversion of algal biomass into biofuels, cosmetic products, biochemicals, food feed, and also high value in goods or products as such as pharmaceutical product. As a result of its good capacity to grow more quickly and far, and provide a lower risks to the food supply chain, so it is gaining as a uh, more attention as a sustainable biomass feedstock for the biorefinery. The pace of biomass synthesis and the capacity to accumulate biomolecules enables the microalgae to completely replace the petroleum based energy sources or goods and build a sustainable circular bioeconomy. A wide variety of the microalgae produce these high value chemicals such as beta carotene or um, polyunsaturated fatty acid. This kind of high value chemicals, it is produced by the microalgae, which may be used as a storage components or functional components in the bioenergy or pharmaceutical sectors. The four categories of microalgae biomass transformation include thermochemical reaction, biochemical processes, transesterification, very important for the algae biorefinery, and the light energy mediated photosynthesis process by harvesting solar energy, which initiates a series of the reaction to generate protons, electron, oxygen through splitting of the water. So in a algal fuel cells or photosynthetic microbial fuel cell, so these carbohydrates derived from the microalgae are mainly composed of the cellulose and starch and will very little or no lignin present. So these are very simple to hydrolyze or fermented. These carbohydrates serves are readily available carbon source for brewing sector or the production of the biobutanol or bioethanol preparation. So you can see these algae by after the microalgae cultivation, when we are going for the thermochemical processes, you will get syngas, bio-oil, charcoal, bioelectricity, bio-oil. Transesterification, mostly we are getting the biodiesel production. Microalgae fuel cell, from the fuel cell we will also get the bioelectricity. And when we are going for the carbohydrate fractions, from that we are getting the biogas, also health supplement and bioethanol. Protein fraction, health supplement and biogas. Lipid fraction, we are getting lot of polyunsaturated fatty acid. Antioxidants and vitamins are also produced, which are highly used in the cosmetics and pharmaceutical products. Pigments like pharmaceutical cosmetics Minerals are also produced. Those are further taken as a fertilizer. Wholesale biomass as a used for health supplements. Biochemical processes mostly produce biogas, ethanol, and hydrogen. So these are the broad spectrum of the opportunity from the microalgae biorefinery. When it is an integrated algae biorefinery, this is the same thing, that is we are getting lot of chemicals and products from the same feedstock. From the same feedstock we are getting lot of product as a outcome of this biorefinery. So uh, this is the very useful concept of integration of the biorefinery. So integration of the different processes in the whole refinery to get lot of wide spectrum of the chemicals out of the refinery, integrated refinery. So now we are going to discuss about the circular bioeconomy. It is a very important topic for reducing the carbon footprint in the environment. So there is an urgent need to deviate from the classical waste management. Okay, to be more ambitious and articulated biorefinery concept to generate value-added products as well as to maintain the waste management in a proper way. So biochemical bioeconomy synergistically combine both natural resources conversion technology with markets, people, and policies to tackle the societal challenges such as natural resources scarcity, fossil resources dependence, climate change, and unprecedented waste generation, loss of biodiversity, food and energy insecurity, while achieving the sustainable growth. The underlying principle of the bioeconomy is the zero waste emission, thereby promoting the reuse of the all byproducts in the value chain. The convergence of the circular bioeconomy or the bioeconomy in the sense of the waste biorefinery is very crucial for achieving the long-term sustainable social transformations. So here we can see when we are considering the linear economy, it was before persisting in the system. That is, we are getting the seafood like microalgae. You are considering the seafood. Industrial processing is being done. Some waste biomass is being produced. There will be convention and disposal of this waste biomass, and there will be environmental destruction out of the process. So this linear economy is not effective. So we are now proceeding towards the circular bioeconomy. So where the waste biomass, or suppose here is the starting seafood is processed through industrial productions. The waste biomass is green processed, and then from there it is various bioactive compounds are being produced, and from there we are getting lot of bioenergy. This bioenergy is again used for the growth of the seafood. So here we can able to maintain a circular bioeconomy, and we are also getting lot of output products out of this system. So the benefits of the circular bioeconomy is the reduction in waste, reduction in the environmental pollution. Here it is produce valuable biomaterials or biochemicals. There is potential source of this bioenergy because we are not simply discarding the waste biomass, we are utilizing the waste biomass in the chain, and we are valorizing the waste biomass into bioenergy. Also, it addresses the climate change issues. Reduction of the seafood processing cost because we are using the same bioenergy for the growth of the seafood. Sea and increase industrial competitiveness, increasing the resilience and food sustainability of the system. So circular bioeconomy is most crucial to maintain for the sustainable growth of the biorefinery. So last today in the today's class, we will last conclude with the future guidelines for biorefinery. So, a biorefinery should separate all the biomass feedstock components and leading through a chain for several processes to high concentrate of the pure chemical species like ethanol or high concentration of the molecules having similar well identified function. So first, this separation process should be very efficient so that the biorefinery should have the potential to produce those specific biochemicals out of the conversion processes. So separation process is very crucial and should be done very carefully. A feedstock cannot be directly burned without any previous or pre-treatment. Since the aim of the biorefinery is to increase the value of the different biomass components as material and energy source, so the most desirable option is to send for to combustion, right, or for electricity or heat production purpose. Only the residue and the leftover of the previous technological treatments and conversion processes is to be uh, these leftover residues are to be taken care for the combustion, where the whole biomass system should be treated in such way those are highly efficient for the other biochemical production. Okay, a biorefinery should practice at least one high value chemical or one high value material product besides low grade and high volume products. Okay, also, this should produce this kind of variety of chemicals. A biorefinery also should produce at least one energy product besides the other heat and electricity. So it should produce biofuel like any kind of solid, liquid or gaseous product. Any kind of one energy product should be there out of this biorefinery. Biorefinery plants should also aim at running in a sustainable way, that is, all the energy requirement of the several biomass conversion processes should be internally supplied by the production of heat and electricity from the combustion of residue, that is within properly sized set of processes. The leftover residues within the process should be utilized for the combustion for production of heat and electricity, and that heat and electricity should be internally used in those processes where the conversion technologies are being running. Solid, liquid, and gaseous waste production should be minimized. This target can be achieved in two ways: using all the different biomass components for producing a wide spectrum of the multi products in one location, or setting up industrial bioclusters where the material flow exchange among the different plants are promoted in order to transform the downstream residue of a plant into upstream residue of the another plant. So there is bioclusters, industrial scale bioclusters can also be taken as a strategy, so that one product or waste product of one refinery can be taken care in the another feedstock product for the another plant, just like we follow the strategy for the petroleum oil refinery. The same strategy can also be followed in the future biorefinery concept to grow in a sustainable way. Mm. So this is all for today's class. Is there any question that you can ask? We will discuss in the next class for different pre-treatment technologies for the biomass in details. So if there is no question further for this class, so I would like to end this session. Thank you for joining. We will meet in the next session. Thank
Okay, thank you.